Hi, this is Ross Kendall. This is my second update on my project titled The Joule Effect Heating of 1045 Steel. So the first thing that I looked at this week was doing a cross-section of a steel billet. So this is the cross-section that I made with dimensions 0.05 meters by 0.05 meters. The cross-section is broken up into quadrants, so the actual cross-section would be 0.1 meters by 0.1 meters, but for the purpose of modeling, it makes it easier to make it break into quadrants. So the boundary conditions I made for this are symmetry boundaries on the bottom and left-hand side, and then on the top and the right, you have natural convection with the air at 25 degrees C. One of the other things that I was tasked to find out this week was a realistic amount of wattage required to heat this thing up for my application. So based on complete insulation, this number would basically match what I found in literature. And what I found in literature said was that over the course of 60 minutes, the goal was to heat up the steel up to 800 degrees C. Some of these people did it in ovens in a lab, and I saw some others for industry things too. So it's controlled. So basically, if this was insulated, this is the amount of heat that would require to do 60 minutes heated up to 800 degrees C. So I made this in COMSOL, and this is what I got. So this is the temperature at time 60 minutes based on the position of the cross-section of the billet. And obviously the top and right hand boundaries, you see a lot less heat than the middle because of the natural convection. But even after 60 minutes with that amount of wattage going in, we were only seeing temperatures up to 240 degrees C. So that wasn't going to cut it. So I need to go back and basically increase the amount of wattage going in order to get this up to 800 degrees C. So I did that, and this was the number that was required to do that. So that basically figured out, based on this, I can figure out how much current I would need in order to heat this thing up over 60 minutes. The next thing that I started to do was looking at a cylindrical piece of steel. So this 1D line here would represent the radius of a cylinder. The left-hand side would be the center of the cylinder, and the right-hand side would be the edge of the cylinder that would see natural convection with the air. So if this thing had heat generation across it, but had this natural convection term, people have gone and figured out exactly what this solution is, and it's shown here. And so with some help from Ernesto, I was able to model this in both Maple and to find an analytical solution, and in COMSOL to find a numerical solution. And as you can see here, there's some agreement between the two. So my goal is to export some of these and put them against each other just to show that. And then I want to assume some information that wasn't representative to my problem. So I want to change basically the times on here as well as the radius of the cylinder, because this wouldn't match what I would expect in real life. But at least I know now that the model is working, and that's good. And then for next week, I'd also like to look at if this steel billet was at 800 degrees C, and I assume that this whole thing was 800 degrees C. If we were to quench this thing really fast by putting it in water at 25 degrees C, how long would it take for the thing to cool down? And I can basically mess with the water temperature, and I might even look at some different liquids in order to see how fast we can cool this thing down. Because when you get fast cooling, you get better property retention. So this is kind of where I'm going with my project next week. I'm looking forward to figuring out the results. Thanks.